Welcome back all of you. In the last lecture, we have started fourth module on critical state soil mechanics. We were dealing with the introduction of critical state soil mechanics. We will continue with that lecture in today's lecture as well. In the last lecture, we have understood a few aspects of critical state which we already know initially, but we are trying to understand in the context of a framework. So, we have not actually discussed the entire aspect of critical state line. So, we will focus more on that in today's lecture and see where it position itself with respect to the normal consolidation line or the swelling reloading line. Okay. So, today's lecture will focus on critical state, normal consolidation, heavily over consolidated state and lightly over consolidated state. Why this is important is we need to understand what is the starting point of a given soil, or rather I would say state of the soil with respect to critical state. According to critical state framework, we know that the failure would happen when the soil state reaches critical state. That is how we define it. Now, where the soil position is initially with respect to critical state will help us appreciate or understand better in what manner or in what amount of what is the factor of safety that is available before failure. We have already said that normally consolidation line is the rightmost boundary. It can be normally consolidated or we can say it as isotropic consolidated. Whatever be, it remains the same. Only thing is for triaxial we are specifically interested in isotropic consolidation. So, for all practical purpose our normal consolidation line we can treat same as that of isotropic consolidation line. So, in V ln P dash we can draw NCL, we have already seen that, and that is the rightmost boundary, and this NCL has a slope of lambda. Now, the space which is towards the left is always the lightly over consolidated or heavily over consolidated depending upon what amount of unloading the soil has undergone with respect to its past maximum pressure. The past maximum pressure lies on normal consolidation line or isotropic consolidation line, from where it is unloaded, which creates lightly over consolidated state or heavily over consolidated state depending upon how far the state of the soil is with respect to NCL. So, this is the leftmost part is LOC and HOC. Now, even though we know all these facts, it is very important that we visualize this in the critical state framework. Consider critical over consolidation ratio line which separates lightly over consolidated and heavily over consolidated. Now, we have already seen in module 2 that the behavior of heavily over consolidated is fairly different from that of the normally consolidated response. Understanding this response is very important to understand critical state framework as well. So, first we need to understand what separates heavily over consolidated from normally consolidated. Now, there is another category which is lightly over consolidated, which resembles its behavior more towards the normal consolidation, means it may not exhibit peak. So, where should we draw a line so that it separates the normally consolidated or maybe lightly over consolidated from that of heavily over consolidated, and that is given by critical over consolidation ratio line. So, over consolidation ratio helps us to understand how much or what is the degree of over consolidation the soil is subjected to. Now, let us understand it to be a line, that is critical over consolidation ratio COCRL, to be a line which is parallel to NC, because then the ratio will be the same. Now, this line also has an inclination of, or the slope of lambda. Now, the portion, now what it means is, this particular line is the line between lightly over consolidated state and heavily over consolidated state. So, this line separates it. So, any state which is on this particular line on the left of COCRL will be HOC, and towards the right of COCRL will be lightly over consolidated, and on this line it is NCL. So, that is marked here. In general, now where does the critical state line fall? So, in general, CSL can be assumed to fall between normal consolidation and COCRL. So, the critical state line falls somewhere in between NCL and COCRL. Now, we need to understand this, that these are all certain concepts. Now, according to that, it is somewhere here. So, this portion is lightly over consolidated, towards this side also lightly over consolidated, towards this side also lightly over consolidated. Now, whether a lightly over consolidated soil will exhibit peak or not, these are all dependent on that specific type of soil, but definitely towards left of COCRL it is going to exhibit a heavily over consolidated behavior. The value of critical over consolidation ratio depends on the soil type. So, what is the over consolidation ratio? Below which it is LOC and above which it is HOC. It is dependent mostly on soil type, but in general COCR, that is critical over consolidation ratio, can be considered as 2. In most of the cases, for practical purpose, we can consider the over consolidation ratio as 2, which is termed as critical over consolidation ratio. Now, below 2, if the OCR value is less than 2, we consider it to be LOC, and above 2 can be considered as HOC. These are all some bare idea, like it is not a very strict philosophy. It is a kind of a rule of thumb below which it is considered to be LOC. The region on the right side of COCRL, now this COCRL is the reference, towards the right side is called wet side. Now, this particular definition of wet side, dry side we have seen in compaction curve. What is towards the right of OMC, we call it as wet side of optimum, and towards left it is called dry side of optimum. Similar to that, it is defined that towards the right side of COCRL it is wet side, and towards left it is dry side. Now, wet side, dry side I am introducing because the basic philosophy of critical state soil mechanics put forth by Schofield and Roth, they also use these terminologies. So, it is important, or so it is good that we understand these terminologies better. So, that is why I am introducing, and as such wet side, dry side does not have much significance if you understand it is towards right or left. So, the region on the right side is wet side, and towards left of COCRL is called the dry side. Now, you need to keep in mind the difference between COCRL and CSL is not much. So, sometimes you can find certain discussions wherein the wet side and dry side is also talked in terms of critical state line as well. So, we can say that dry side of critical state line or towards wet side of critical state line. In fact, the over consolidation ratio separating LOC HOC is very it is marginal. So, one can always say that towards dry side of critical state line it exhibits HOC behavior. So, wet side, dry side, here we are specifically discussing with respect to critical over consolidation ratio line, but keep in mind one can also refer to in terms of critical state line as well. Now here it is marked as wet side where specific volume, that is V, is greater than V critical. V critical is the critical void ratio with reference to COCRL, and if it is less than COCRL, then it is dry side. Keep in mind, we can also refer to Vc as the specific volume along the critical state line as well. So please keep in mind this difference. In general, the definition is like this, but one can also refer Vc as the specific volume on critical state line. Okay. Now let us see some important aspect related to undrained strength. We have discussed this. SU is the undrained shear strength of soil, which we discussed in the module 2. So we will see in terms of critical state framework, how does it look like. Now we know the relationship tau f, which is the failure state, and for critical state framework the failure state is same as the critical state tau Cs, which is equal to sigma dash Cs tan phi dash Cs is applicable for effective normal stress. Now this relationship, it is familiar to us, and we talk this in terms of critical state or the effective normal stress. Now undrained strength, we need to represent this differently, which is not similar to that of this particular relationship. This particular relationship we know it is more like a Mohr Coulomb failure envelope with inclination of phi dash Cs. So tau versus E, how does it look like? So this is shear stress up versus void ratio, and this is the critical state line. Now here T, this in the case of undrained shear strength, we have tau Cs, that is the critical state strength is equal to undrained shear strength, and the void ratio corresponding to that is ECS. Now we can see here that strength decreases with increase in E, as can be seen here. Now there can be SU here, there can be SU here. So as E increases, the value of SU comes down. Now we know that the relationship GW is equal to SR into E. Now this is a saturated state, G is a constant. So as E increases, W increases. That means W and E is related. So it also means that with increase in E, SU decreases, which is very correct also, as the water content increases, the SU value comes down. So strength is thereby related to W as well. We are talking about undrained shear strength very specifically, and undrained shear strength is highly sensitive to its initial condition in terms of E or W. Now we also know SU refers to the strength when soil is sheared without change in W. So it is at constant W condition we are doing the shear test. So there is no change in W. Why? Because there is no change in drainage condition, and hence the E also remains constant. So we can write tau F tau Cs is equal to SU, which is the undrained shear strength. We also have the relationship tau Cs is equal to sigma dash Cs tan phi dash Cs. Now in this case we can write tau Cs is equal to SU. So substitute for tau Cs equal to SU. Now whether this equation holds good or not. So based on our previous understanding, please refer back to module 2. We have what we have discussed when we discussed about UU test, like we have only one effective stress circle, because of which we are not in a position to define the effective stress Mohr Coulomb envelope. But while discussing that, we also have seen if phi dash Cs is known, one can always draw the Mohr Coulomb failure envelope for the very one effective stress circle that you obtain from the UU test, which means there is a point of intersection between the effective Mohr circle envelope with the Tresca envelope which is given by SU. So, there is a point where it intersects. So, this particular equation holds good and that can be explained in this particular manner. So, this is tau versus sigma dash and this is the Mohr Coulomb failure envelope. Now, this is the Tresca failure criterion wherein SU is the undrained shear strength. So, this point is what we are discussing about. So, this point, this particular equation is very much valid. So, SU is equal to sigma dash Cs tan phi dash Cs. So, we can write sigma dash Cs is equal to SU upon tan phi dash Cs. We also have the relationship ECS is equal to E gamma minus Cc log sigma dash Cs. This comes from our previous lecture. Okay, so, please refer back. So, we can write ECS is equal to E gamma minus Cc log this sigma dash Cs, we can substitute it here. So, we have Su upon tan phi dash Cs. So, we can write this goes on the left side, we have Cc log Su upon tan phi dash Cs is equal to E gamma minus E Cs upon Cc. So, here you are relating Su as a function of ECS and other parameters. So, here you can see Su changes with change in E or W, which we have already explained. Since it is changing with the state, it is not a fundamental soil parameter, and that is where we have started off with C dash and phi dash. So, for undrained shear strength, it still holds good that it is not a fundamental soil parameter. Su is a state dependent parameter. So, what is the state of the soil? For undrained shear strength, it is more dependent on state. State means how and where the soil initial point is positioned with respect to the critical state line. So, that is defined by E or W. So, the state is defined by void ratio. In the critical state framework, we define it using void ratio. So, initial void ratio gives where it is with respect to the final state which is on the critical state. So, that is why Su is known as the state dependent parameter. So, we will come to what is meant by state in the subsequent slide. So, critical state, now let us see in QP dash format. We are explaining in two ways. Critical state, directly we know it comes from tau sigma dash response, whatever we know from module 2, and all those concepts remain same in QP dash framework, because you will see later the critical state is mostly defined in terms of stress invariance, which is QP dash. So, we will be discussing both. First we will discuss in tau sigma dash format, and then we will come to QP dash till we introduce all the concept. Further on we will deal only with QP dash V space, or you can also write it in terms of QP dash E, because E and V is there is only a difference of 1. So, 1 plus E gives V. So, both are valid, but let us, while understanding critical state framework, let us discuss both. So, whatever we have discussed now in terms of tau sigma dash E, we will see that in QP dash and V. So, response is similar to tau sigma dash E. Now, when we discussed QP dash V in the previous lecture, we have not discussed the failure state, that is what is how QF and P dash F is correlated. So, we are yet to discuss that, so that we will discuss now. Now, this particular response we have not discussed in the previous lecture. So, it is QP dash and critical state line is given by this. This is nothing but the KF line that we have seen before. Now, how it becomes critical state line? Because here the phi dash considered is phi dash Cs. So, that is why it Kf automatically becomes a critical state line. Let us assume P dash F is equal to P dash Cs. Now, critical state, the failure state is same. So, P dash F is equal to P dash Cs, and for which Qf is equal to Qcs. Now, this is related. Now, the slope of the critical state line is given by capital M. So, critical state line in Qp dash is defined by Qf is equal to M into P dash F. Very important expression which you need to keep in mind. So, critical state in Qp dash V space is defined as Qf is equal to M into P dash F. It is also good to write Qcs is equal to M into P dash Cs. So, both are valid. What is M? M is the slope of failure line in Qp dash plot, and we already have defined or we have derived this expression for the slope in Qp dash. Again, please refer back, we have already done it. And for compression case, it is 6 sin phi dash Cs upon 3 minus sin phi dash Cs. Now, you can see here we are denoting it by phi dash Cs. So, that is why here the failure line Kf is equal to critical state line. Now, let us see this in terms of V ln P dash. Now, this is the NCL with a slope of lambda. The critical state line is positioned like this because we know the rightmost boundary is NCL and there is no state beyond NCL. Now, this is the unloading reloading line with a slope of kappa. Again, we have already discussed this. Now, let us say here P dash F is equal to P dash Cs, which is lying on the critical state line, where Vf is equal to Vcs. Now, all the important parameters are defined, that is P dash Cs, Qcs and Vcs. Now, we already have a reference line or the reference point on every line which corresponds to P dash equal to 1 kilopascal. So, here or NCL it is N naught, for the unloading reloading line is V kappa, and for critical state line is capital gamma, which can be represented. So, all the initial states of the line has been defined, based on which the equation for this line NCL and critical state line can be written. So, we can write the equation for critical state line in V ln P dash as gamma, that is this point, minus lambda is the slope because this is also lambda, minus lambda ln P dash F. Now, P dash F means P dash Cs. So, every point on the critical state line can be defined using this expression Vf is equal to gamma, which is corresponding to 1 kilopascal, minus, and then it depends upon where actually the point is. So, this is the P dash F. Here the parameters lambda, capital M and gamma are independent of initial state. Why? Because these are the parameters which represents the critical state line and can be considered as fundamental soil parameters. Earlier we have understood in tau sigma dash space, tau sigma dash E space, that Cc, which corresponds to lambda, and the other parameters, it can be used for defining the fundamental parameters of soil. So, similarly in QVP dash space you can write lambda, m and gamma, these are the fundamental parameters of soil and it can be considered in the case of critical state framework. M and gamma, that is the slope m and gamma measured in compression is different from extension, that we have already seen. The slope of Kf line in extension is different for QP dash plot. So, similarly m is also marginally different in the case of extension case. So, now we are basically discussing with reference to compression line. So, we will not bother about that right now. Also, we know that in the previous slide we have discussed about undrained shear strength. Now here also we can very well define undrained shear strength QSU is equal to QF by 2. Now QF is sigma 1 dash minus sigma 3 dash divided by 2 is the radius of the circle, which gives you Tresca criterion. So SU is very much equal to QF by 2 and QF is equal to M into P dash F by 2. So we can also write Ln 2 SU by M is equal to gamma minus Vf by lambda, the way we have written previously in terms of log. So how this is possible? This is possible because you are writing the expression for Ln P dash F, which is equal to gamma minus Vf upon lambda, which is equal to Ln P dash F, and P dash F is nothing but 2 SU upon M, which from here. So that gives the expression for SU in terms of critical state parameters. Okay. So now let us further try to explain. Every point in QP dash plot has the corresponding point in VP dash. So that is true, whatever we are having here, wherever we are taking a point here can be correspondingly marked in the V ln P dash plot as well. Failure is defined by a single surface in VQP dash, which is the critical state of that particular soil. Now unloading reloading line crossing critical state line in VP dash plot does not mean any failure condition. Now this is something which I am explaining because when we discuss this in the normal classroom, we have found that some students always have this doubt that you can see here critical state line is placed here. Now from here the unloading line, it goes and it crosses the critical state line. Now sometimes there is a misconception that it is crossing the critical state line, so the failure has already occurred. It is not true. Critical state line is only a relative position of the failure condition. The unloading reloading line, it only determines the stress history of the soil. So crossing this critical state line in, please underline, in VP dash or V ln P dash plot is not a failure condition. Obviously when it crosses or when it touches the critical state line in QP dash plot, it is the failure condition, not in V ln P dash plot. So please do not confuse yourself. This with respect to V ln P dash, it is only the relative position or the state of the soil when I say that it is on unloading reloading line or on NCL, it is only the state of the soil, the initial state of the soil, and during shearing it moves towards the critical state line. It is not that merely this crossing, it does not mean that the failure has occurred. It only indicates the initial state of the soil with respect to stress history. You know that different points on the unloading line with respect to the given NCL gives different OCR. Whether the soil is on wet or dry side of the critical OCR line. So that is the only purpose of these points. Failure is entirely governed by effective stress path when it touches the critical state line, which comes from this particular figure. So when the effective stress path when it starts from a particular point and when it reaches the critical state line, then that explains whether the failure has occurred or not. For failure to take place, soil has to yield first. So for this also we know, for failure to take place the soil has to yield first. That means we need to introduce another concept which we will see shortly, that we need to define what is soil yielding. Now when we discussed in the case of module 2, we never discussed this point explicitly, but it is there. but we are not discussing that explicitly. But in this module, we need to clearly state when the soil is going to yield. So, without yielding, failure cannot take place. So, I am not going into the details right now. You can underline this fact that for failure to take place, soil has to yield first. This particular understanding is extremely important when you try to understand the behavior of OC. Okay. So, let us hold on for the time being about this yielding, but make sure that we understand that for failure to take place, soil has to yield first. Okay, so that is all the preliminary discussion about critical state in both the formats, that is tau as well as QVP dash format. Now we will discuss a bit about normalization of VQP dash plot with respect to some initial condition or some specific parameters, so that the comparison becomes easy. Consider a point P. The state of P is defined by, so this is the point P. Now state of P can be defined by what is the, you can assume a line which is parallel to NCL with slope lambda passing through P. So the state of this particular point P can be defined by P dash P, VP as well as QP in QP dash plot. Now corresponding to this particular VP, if we draw a horizontal line, we can also find P dash corresponding to that on the critical state line, and that is P dash PC. Now the value of specific volume corresponding to 1 kilopascal on the line through P is given by VP lambda. The effective stress corresponding to VP on NCL line is given by P dash Pn. Now P dash represents it is effective, P mean stress, this P represents that it is with reference to point P, and N represents that it is on NCL. Similarly here C represents it is on critical state line. So there are certain reference points now. VP is the specific volume for point P. Now P dash corresponding to VP has been marked, and that the normalizing parameter is P dash PC and VP lambda. So these two parameters. Now for every point in this space, you can find a corresponding VP lambda and P dash PC. Now you may be wondering why the normalizing parameter is not P dash P, because this P dash P is dependent on the position of the point P, whereas P dash PC is a more it is a more stable point, because for every P you are considering the point or the location of this point with respect to critical state line. So that is why P dash PC can be a good normalizing parameter. Obviously this 1 kilopascal reference is also a very good normalizing parameter. Now P dash Pn is also used as normalizing parameter. So what is the distance of point P from NCL, that is P dash Pn. So this can also be used as a normalizing parameter, but rather than normally consolidated line, critical state line is of more importance. Why? That distance actually represents the factor of safety. So for all practical purpose, the normalizing parameter can be considered as VP lambda and P dash PC. We can write VP, that is specific volume along this line, is equal to VP lambda minus lambda ln P dash P. Now when we substitute ln P dash P, that is this particular point, we are discussing VP of point P. So VP of point P is equal to VP lambda minus lambda ln P dash P. Now when you know the initial point P dash P is known, VP is known, VP lambda can be determined. So that becomes a reference parameter. So, Vp lambda is equal to Vp plus lambda ln P dash P. So, Vp is equal to gamma minus lambda ln P dash Pc. Now, Vp is this particular point. So, you have this Vp on critical state line as well. We can very well write Vp is equal to gamma minus lambda, lambda is the slope of this lambda ln P dash Pc, because this is the reference point. This equation we have already discussed previously for critical state line. So, Vp is known now. Vp depends on the position of P, gamma is the critical state parameter which is known, lambda is known, P dash Pc can be determined. So, ln P dash Pc is equal to gamma minus Vp upon lambda. So, both the normalizing parameters can be determined. Now, when you normalize the whole of the VQP dash plot, how does it look like? So, let us normalize with respect to P upon P dash Pc and P dash upon P dash Pc. Now, how does it look? By normalization, both critical state line and NCL will appear as a point. Now, both instead of a line, it becomes a point. How? So, let us say that this is the point which is the representation of that particular soil in Q P P dash Q upon P dash Pc, P dash upon P dash Pc space. This is the normalized plot. So, this is the point corresponding to CSL. Let us see how. Now, along critical state line, this line P dash is equal to P dash Pc. So, any point we take, let us say take this point, again this is P dash Pc. So, P dash is equal to P dash Pc. So, P dash upon P dash Pc is equal to 1. So, this is not going to change. So, this 1 is represented by this particular point. So, you have a line along P dash upon P dash Pc equal to 1. So, that is fixed for a critical state line. Now, QPF upon P dash Pc is equal to m. How? That is QP upon P dash F, that is QF upon P dash F is equal to m. Now, P dash F is nothing but P dash Pc because it is on the critical state line. So, we know that that particular ratio is m. Now, for critical state point, we know that Q upon P dash Pc upon P dash Pc is equal to m. Why? Because here P dash upon P dash Pc is equal to 1 in this particular case, and Q upon P dash Pc or this particular one is already equal to m. So, this becomes m. So, where you find a particular point with a slope m which intersects this particular line is the point of critical state line. So, that is how we can say that critical state line is a point in this normalized space. Now, for considering NCL to be isotropic, let us say that the initial point is isotropic. So, in that case sigma 1 dash minus sigma 3 dash is equal to 0, that is Q is equal to 0, hence Q upon P dash Pc is equal to 0. So, this Q is 0. So, NCL will be represented by a point anywhere on this particular line where it is 0. Also, P dash Pn upon P dash Pc is a constant. You can see that P dash Pn is this and P dash Pc is this. This remains always a constant wherever you take. So, that constant is not going to change. So, always it can be represented by this particular point, as so NCL is represented by a point. Now, depending upon the different type of soils, the relative position will change, that is along this it will change or along this it will change, but these CSL and NCL can be represented by a particular point. Now, we have discussed about state of the soil. So, we will discuss state of the soil in detail and the state parameters. Now, state of the soil is relevant for a given point. Now, here the reference point is P. State of soil also play a role in governing strength and stiffness along with E, W, P dash and OCR. So, whatever be these parameters, that is going to define what is the strength and stiffness of the soil. So, similarly, it is important to understand how state of the soil also play a governing role in defining the strength and stiffness. It is one and the same, because once you know this, you are defining the state, but the parameters in V, L and P dash in terms of state parameters we will define. State of the soil defines the initial point from CSL. You can see here this point P, how distant it is from CSL is the kind of factor of safety. Consider point P. So, this we have already done. Vertical distance of point P from critical state line is SV. So, when we define state of soil, we are defining what is the state of this particular soil initially with respect to critical state line. So, that is why we are defining the vertical distance of point P from the critical state line. You can see this red line. Now, since these are parallel, this is also the same as this distance, and this particular distance is represented by SV, which is the state parameter. So, that is what we are going to define. This state parameter is what we are going to define. So, the vertical distance is SV. Now, SV can be written as gamma minus Vp lambda. What is gamma? This distance is gamma and this distance is Vp lambda. So, SV from the geometry you can very well write gamma minus Vp lambda. Horizontal distance of point P from CSL is given by, this is on ln scale, so LNSS. So, this is the horizontal distance. Now, LNSS can be written as Ln P dash PC minus P dash P. So, SS can be written as P dash PC upon P dash P, this P dash PC upon P dash P. You can see that this is very much similar to the definition of OCR. OCR is with reference, instead of P dash PC, it is with reference to the stress state on the NCL, which is called as yield stress. So, here SV upon ln SS is equal to lambda. Here if you consider this particular line and this, so this is ln SS, this is ln SS and this is SV. So, SV by ln SS equal to the slope which is lambda. So, that is given as lambda. So, we can always write SV is equal to lambda into ln SS. Okay. So, this is the relationship between the state parameter. So, SV and SS are called state parameters of that particular point, or what the soil state is with respect to critical state is given by the state parameters, and the vertical and horizontal are SV and SS. State parameters are related to critical state line. SS is very similar to OCR. This definition of SS is very similar to OCR. In OCR is related to normally consolidated line, whereas SS is related to critical state line. So, summary of critical state parameters. Now, what we have done is, in the name of introducing critical state, we have discussed quite a lot of things in these two lectures. But what is very essential as we move forward when we interpret critical state soil mechanics, so that summary we are providing here. So, whatever we have learned, finally these facts what we are going to discuss now is very important. So, only effective stress path is considered. You have ICL or NCL. ICL means isotropic consolidation line, or NCL with slope lambda, CSL with slope lambda, unloading reloading line with slope kappa, the initial point reference P dash equal to 1 kilopascal, N naught, gamma and V kappa. And we need to see only effective stress path is considered for defining failure. So, then we have Q P dash plot, where QF upon P dash F is given by slope M. So, M, lambda, kappa, they are important. CSMM utilizes the index properties determining CC from liquid limit, because CC is the one which we get from the consolidation plot. So, this Cc is very important, and we know that Cc can be determined from liquid limit. So, CSSM utilizes index properties in one way or the other. Then effective stress, that is sigma n dash, that is the normal stress, or the consolidation stress sigma dash, which is always in terms of effective. Stress invariance, because Q and P dash we are considering, and stress path, whether it is drained, undrained, how it moves. So, CSSM utilizes these information as well. The primary consolidation data, that is Cc, Mv, lambda and kappa. Shear strength Q, P dash, capital M and phi dash Cs. So, all these we have discussed, and critical state framework utilizes these properties. Isotopic consolidation or normally consolidation line, which is given as this, where it is defined as N naught minus lambda ln P dash. Unloading reloading line, which is defined as V is equal to V kappa minus kappa ln P dash. All this we have discussed, I am just summarizing it. And critical state line CSL is defined as Vf is equal to gamma minus lambda ln P dash f. So, you can see that with reference to this, here you are adding the subscript f for critical state line, and the additional one what is needed is Qf is equal to m into P dash f. So, these are the essential relationships which we have to keep in mind for dealing with critical state framework. We also need to understand the relationship of Cc and Mv with lambda and V, because we need to cross compute these as and when required. We know that Cc is equal to minus dE upon d log P dash from our initial definition of Cc, and that corresponds to normally consolidated portion. V is equal to 1 plus E, dV is equal to dE, substitute for in the previous expression Cc equal to minus dE is replaced by dV, and d log P dash can be written as 1 by 2.303 d ln P dash. Now, d ln P dash is 1 by P dash into dP dash. So, that will give you Cc equal to minus 2.303 P dash, that goes into a numerator, dV upon dP dash. Now, we have the expression for normal consolidated line as V equal to N naught minus lambda ln P dash. dV, if you differentiate this, you will get minus lambda dP dash by P dash. So, we can write dV upon dP dash is equal to minus lambda by P dash. Now, you can see this expression, and this dV by dP dash can be substituted. So, Cc can be written as 2.303 lambda. So, knowing Cc, lambda can be determined. So, Cr, that is for unloading reloading line, the same equation holds, only thing is instead of lambda it becomes kappa. So, Cc and Mv relationship with lambda and V, we will continue. We need to find out the expression for relationship for Mv. So, Mv again from the basic definition we have minus dE upon 1 plus E naught. E naught is the initial void ratio upon dP dash. So, Mv is equal to, again substituting, we have dV 1 plus E naught is initial specific volume V naught dP dash. dV by dP dash we know that is minus lambda by P dash. So, Mv is equal to lambda by V naught P dash. So, parameters lambda, M, gamma are critical state parameters in V, Q, P dash space. Please keep these relationship what we discussed as summary in your mind, because these are very important as we move further. These parameters can be considered as fundamental soil parameters. Some additional note on critical state before we wrap up the introduction part. The strain required to reach critical state depends on the initial soil state, whether it is on wet or dry state of critical. Soil sample strain without change in shear stress, effective stress and volume at critical state. So, there is a shear straining happening at constant condition. Shear strength tests are normally terminated at strain less than 20%. It depends upon the codal provision what is the termination criteria. This strain may not be sufficient to achieve critical state for soil samples on wet side of critical. Again I told that these are all concepts put in place. Now in reality what actually is happening to the soil we really do not know. So we have some termination criteria at a high strain, and high strain we consider it to be maybe less than 20%. So we presume that the state what we define as critical state has been achieved by the soil during shearing, but we are not sure. Now we also need to keep in mind that even at 20% strain there are possibility that the soil has not reached its critical state. So phi dash that you define based on this 20% strain actually may not be phi dash CS, it may be even less. So what actually it is we do not know, but we presume it. Now for wet side of critical state, it may so happen that it will not reach the required critical state at 20% strain. Now wet side of critical means what? It is mostly referring to normally consolidated or lightly over consolidated state. Now for this there is a progressive densification that is happening upon yielding. After yielding it is strain hardening. So it can build up more and more. So that is the possibility why we say that it may not reach to its critical state. Whereas in the case of OC state, what happens with shearing, there is a dilation. So it is a progressive softening that is happening, that soil particles are disintegrated or separated from each other. So here the critical state is fairly easy. The strain may be sufficient for the whatever 20% what we discussed. This strain may be sufficient for soil samples on dry state. Dry state means nothing but the heavily over consolidated state. It is ideal to conduct shear test on lightly over consolidated samples for determining critical state, since the initial state is close to critical state. So if you are planning to obtain the critical state parameter, one suggestion is that if the soil is lightly over consolidated, then fairly it is easy for the soil state to reach critical state. If you see that in terms of V, L and P dash plot, you can see that LOC is more close to critical state than HOC and NC. So if we start the shearing at lightly over consolidated state, it is fairly, we can say that by 20% strain, yes, there are all possibilities that the soil would reach its critical state. Critical state line passes through origin in QP dash plot, no strength at zero confinement. Now if there is cohesion, definitely that is going to be there at zero confinement, that is what we know. Now in QP dash, if we are representing the KF line in terms of critical state line, it passes through origin. Now what is the logic here? If there is cohesion, does it mean that it is not considered? Let us see what actually does it imply. So there is no strength at zero, we are not considering any strength for the soil at zero confinement. That is, we are discussing with respect to critical state line, that we have to keep in mind. In case of true cohesion, okay, we are not discussing about apparent cohesion, but if there is true cohesion, soil will exhibit some sort of cementation characteristics. And if there is cementation characteristics, obviously there will be some strength at zero confinement. There will be strength at zero confinement, but in the case of critical state line, we do not consider this. Why? It is because the strain required to reach a critical state is enough to break the true cohesion or cementation. So when the particle undergoes shearing, it is undergoing volume change, and we know that under critical state there is the movement of soil particles more like a fluid, frictional fluid we call it. So there is a turbulent motion of particles. Now when we define such a situation for critical state, it is very implicit that the particles bonding need not be considered at critical state. That is a logic which states that there is zero strength at no confinement condition. So, critical state line passes through the origin in QP dash plot. It is hard to exactly achieve critical state during shear test for the reasons we have already stated. It is often assumed that critical state has reached for the strain level considered in the test. Now, the concept of critical state is also a hypothesis, and in the testing, in the actual practice for its implementation, we presume that the termination criteria that we adopted, if the soil has not failed, that particular strain level corresponds to critical state. So, whenever we are using this termination criteria, we need to keep in mind that it is based on the assumption that we are following this. So, let us summarize the last two lectures where we have discussed or we have introduced the critical state soil mechanics. Critical state soil mechanics is a concept that integrates consolidation and shear strength behavior for defining failure state, which has not been done in Mohr Coulomb failure envelope. The 2D representation of void ratio versus effective stress and shear stress versus effective stress is integrated to obtain 3D representation of critical state. We have not done this yet. That will be towards the end of this module that we will see how to integrate the concept. According to CSSM, all soils will fail on a unique failure surface defined in QP-E or QP-V space. Critical state in general is attained at shear strain greater than 10%. Why instead of 20% I have used 10% is in some codal provision it is 10%, in some it is 15%. So, in general less than 20% is the understanding. Critical state parameters can be considered as a fundamental soil property. Accordingly, phi dash CS, because we discussed it in terms of tau sigma dash E plot. So, phi dash CS E gamma CC can be considered as fundamental soil parameters. Normal consolidation line NCL, unloading reloading line and critical state line are important for defining CSSM. We have seen that. In QP-V space, slope of NCL and CSL is lambda and the slope of unloading reloading line is kappa. NCL forms the right side boundary for the soil state to exist. We will be discussing this again in the subsequent lectures. Left of NCL is LOC and HOC. Importance of OCR and yield stress ratio discussed. Soil bulk stiffness is dependent on lambda and kappa depending on whether it is loading or unloading, and hence it is not a fundamental parameter. Critical over consolidation ratio line is the boundary between LOC and HOC. The region on the right side of COCRL is called wet side and left is dry side, which is heavily over consolidated. Undrained strength expressed in terms of CS parameters, both cases for tau space as well as QP dash space has been discussed. How to normalize VQP dash plot has been discussed. State of soil and state parameters has been defined. Parameters lambda, m and gamma are critical state parameters in VQP dash space and are fundamental soil parameters. Finally, we need to keep in mind that critical state is a concept and there can be departure of this concept from actual reality. It is practically difficult to assess whether the soil has reached critical state during shearing. In most cases, it is assumed that the soil reached critical state during shearing, that is at high strain condition, which is practically greater than 10%. So, that is all for today's lecture. Now, we have introduced critical state framework. In the next lecture, we will see more about 2D representation. Stage by stage we will progress, and then finally we will discuss about 3D formulation, how to integrate the concept. So, that is all for now. Thank you.